Okay, so we are being recorded. It's my pleasure to introduce our today's speaker, Marco Carfagnini, who is a recent addition to our school at the University of Melbourne. So he started working here, I believe, September?
Yeah.
2024. He did his PhD University of Connecticut. It was, I think, 2022. And then after maybe a couple of years, San Diego, he ended up here. Now, Marco asked me today whether I knew Misha or Michael Gordin, who was the father of his supervisor, PhD supervisor. And indeed, I checked, I looked up the picture and recalled, yes, I knew him. And so I knew his semi-scientific grandfather. And moreover, I knew very well Marco's semi-scientific grandfather, who was Ildar Ibragimov, who was the supervisor of Michael Gordin.
Oh.
Okay, so Marco, please, the screen is yours. The title can be seen on the screen. 50 minutes and then questions. Thank you.
Awesome. Thank you. Thank you, Kostya, for the invitation. So yeah, as you can see from the title here, I'll be talking about small fluctuations in analysis and geometry. So the first part is going to be more about just small fluctuations in general. We'll see a few examples, mostly for stochastic processes. And then the second part of the talk, I want to focus on a very recent project on time-dependent spherical random fields. So we'll switch to random fields later. Let's see if this is, yeah. Okay, so just to start, let's say you have a stochastic process, or if you wish, a random field. And what you're looking at this, look at the small ball probability. So this is the kind of object you're interested in. What does it, let me just write it down maybe more explicitly for a Brownian motion. So, because that's the one makes it a bit easier. So let's say you have your Brownian motion Bt. It starts at 0. So what this thing is, you're simply looking at the max 0 t r of a Brownian motion being less than epsilon. So what you're asking yourself is really how fast this probability. So you're fixing, R is fixed, you're fixing a time interval, or if you want some kind of ball, and you want to know how fast this probability is going to 0 as epsilon goes to 0. And the nice picture that you always draw is that you start your Brownian motion, and then you have, oops, disappeared. You start a Brownian motion, you have a ball of radius epsilon here, and you want to know, like, as the radius gets smaller and smaller, how likely is that the process stays inside the ball until some fixed time. And as we'll see, this purely probabilistic expression here does encode some analytic properties of the generator of the Brownian motion. And from the probabilistic point of view, what I'll talk about, I'll try to convince you that this small probability here is highly related with a law of iterated logarithm. This is not the classical law of iterated logarithm. Again, for a Brownian motion, think of this as you're looking at the max. Imagine you have this new process here, which is the max of the process until time r. This is b, sometimes b star r. So instead of being a law of iterated logarithm for a Brownian motion, is a law of iterated logarithm for the max of the trajectory until time r. It goes back to a paper by Chung in 1948. Chung's original proof was for random walks, and then it was proven for a Brownian motion. But what I would like to convince you by the end of the talk is that if you know something about the process, let's say some kind of space-time scaling, then you prove whichever one is easier. And then let's say if you know the small deviation principle, from here you can prove Chung's law, and the other way around. You can prove Chung's law first, and then you get back to just small deviation principle. So probabilistically, they're very related laws. Now, let me give you just a few examples on this kind of laws. So as I said, the first one will be Brownian motion. That's kind of the prototype of the example that we have in mind. The rate in which it goes to 0 is epsilon square for the small deviation, and you see immediately that, so you've got an epsilon square here, and there is a square root on Chung's law, and the intuition, just to convince you why that is the correct rate, this is really just the, if you have in mind the space-time scaling for a Brownian motion, the reason having a power of a half 2 is kind of the reason why I've had 2 here and the square root here. So yeah, that's sort of the probabilistic intuition behind it. The reason why I like this a lot is because the number an is a fairly explicit number, which has some, it's important from an analytic point of view. So this is the spectral gap for the Laplacian. So what I mean is that you're in Rn. So in Rn, you can look at the following boundary value problem. You have half the Laplacian of f equal lambda f, let's say on the unit ball. And then you have f is 0 on the boundary of the unit ball. Then you know that this problem there is a sequence of strictly positive increasing numbers that solve this equation here, 0, lambda 1, lambda 2, and so on. And this number here, an, is exactly the first eigenvalue. So in some sense, the small probability gives you a way, for at least for a Brownian motion, it gives you a way to recover the first eigenvalue for the Dirichlet Laplacian just by looking at this object on the left. So I'll give you a proof of this result here. There are many ways in which you can prove it. I think the very first, at least the first proof that I found of these results relies on Borel-Cantelli sort of type of arguments. I like that proof a lot, but it doesn't give you any intuition why you should see the spectral gap. So I'll show you a different proof that works for a Brownian motion, and we'll comment on that later. But just a little bit more of more examples. Oh yeah, that's a spectral gap. Told you that. Just to show you that in general, the small deviation business could be, there are certain things which are hard, meaning finding the actual value of the constant when you have once you have the small ball probability, finding the value of this number here is usually very challenging. And this is shown by this very simple process. So you're just taking a one-dimensional Brownian motion, you integrate it in time. Oh, there's a typo here. I see that they should be 2/3. They are one the inverse of the other. This was proven almost 30 years ago. The constant C is not known. So the only reason why I wanted to point this example is that usually you're very satisfied if you can prove that the limit exists, you find the correct rate, and you can show that the constant is positive and finite. Finding the actual value of the constant is usually a very complicated business. Even though here they do have some explicit upper and lower bounds, but as of today, last time I talked to Davar, said that it's still, no one knows what say is. I should also mention that there have been a lot of results, a lot by Wenbo Lee on, you can also look at iteration of this interval. So you're taking like n integrals of a Brownian motion in time. That is also known. And the last example for now that I wanted to...
Also the Dirichlet eigenvalue of some generator.
Not in this case. This is a very good point. I'll talk about, there's going to be 2 examples from now But what I'll do is that this process here is not, it's not a Markov process, right? But what we'll see is that you can put this into a bigger process so that it becomes Markov. And then we'll talk about whether you recover the spectral gap or not. In general, spoiler, you might not get the spectral gap. But we'll see that for a class of processes, you do get the spectral gap, but not for this one here. But it's coming in probably 2 slides. But yeah, it's a very good point. The last example I wanted to mention is the Levy area. And this is an example that I like a lot. This is another process, which is also, this is not a Markov process, just looking at this. But I like this result because it is very explicit. So in this case, you actually do know the limit. And I also want to point out the proofs of these two are very, very different. The paper by Davar and Shi is really, if you want, purely a probabilistic type of argument. They use Borel-Cantelli, they use the local time of a Brownian motion. It's purely probabilistic. The paper by Rémillard, it's more on the analytic point of view. So you look at some kind of heat kernel and you do some analysis. So they have very, very different approaches, but they're somehow both, they're both interesting. And kind of to remark what I said at the beginning about the space-time scaling of a Brownian motion, here you are not too surprised to see the scalings here. And this is really a consequence of also didn't tell you earlier, but the iterated Brownian motion, you can easily check that it's got a scaling, a space-time scaling. It's 3/2. And again, this should be 2/3. Levy area scaling is 1. It's 1 here. So the first thing, punchline, is that if you have a process that has some kind of space-time scaling, you usually have an idea of what is the correct rate, what you need to prove. Then you have to prove it. But at least, you're not like wondering what the correct rate is. And again, you also notice that here you've got the exponents are one the inverse of the other. And this, again, it follows from the fact that you can use one to prove the other. You're just going back and forth. And yeah, I did promise one proof. So I'll give you the an analytic proof now, and there's going to be a probabilistic proof later. So I think that balances out. This is a way of proving the small deviation for a Brownian motion. Again, as I said, you can do it in multiple ways. The first step would be to look at your small deviation. What you're going to do is you use space-time scaling to push the dependency from space to time. And once you do that, you're in business, because now you can think of this in terms of exit time. So this is telling you how likely is that a Brownian motion will stay inside the unit ball until this time. Or in other words, how likely is that the exit time, that D is just the unit ball, the exit time from the unit ball is larger than T over epsilon squared. Okay? So you do that. And the reason why you want to do that is because you can write this probability here in terms of the Dirichlet heat kernel. So you can write it in terms of this function here. So what's this function? You can think of it from an analytic point of view is the fundamental solution for the heat equation on the unit ball with 0 boundary conditions. That's one way of thinking about it. Or the way I think it's maybe more intuitive, this is pretty much the PDF. It's a transition density of a killed Brownian motion. So you start your Brownian motion inside the unit ball, and then once it hits the boundary, you're killing it. It dies. So either way you want to think about it, transition density of a killed Brownian motion, or fundamental solution for the heat equation with 0 boundary conditions. The nice thing about this function is that it's smooth, and it does have an eigenvalue, eigenfunction expansion. So you can write a series expansion for this function. And when you write the series expansion, these guys here turn out to be exactly the remember these are going to be the eigenfunctions and the eigenvalues for this problem here. So I like this proof because it tells you pretty much where the spectral gap is coming from. It's coming from the expansion of the transition density of a killed Brownian motion. And then once you have this expansion here, just take the logarithm and you get you pretty much get what you want. So just to wrap up this introductory part, we've got this kind of, didn't stress it for now, but we'll come back to it later. Small deviation and Chung's law are kind of equivalent in some sense. And then for this proof to work, you're using two things, some kind of space-time scaling for your process, and then some analytic properties of the transition density. Those are the main techniques. Now, before, as I promised that eventually we were gonna talk about time-dependent spherical random fields. We'll get there. But before, what I want to do is, so I've showed you three examples, a Brownian motion, an integrated Brownian motion, and the Levy area. So what we want to do now is, so I've told you that for the Brownian motion, you get, where is it? For the Brownian motion, this is a nice Markov process. You get the generator here. Now, these two, they're not Markov processes. So what we're going to do now is we're going to turn them, we'll see how we're going to make them into two Markov processes so that we can talk about the generator of those processes and then see whether the small deviation gives us some kind of analytic properties or not. I also think this is a very nice, it's very interesting that, like, let's say here, the Levy area, as I said, this is not a Markov process, but if you couple the Levy area with a two-dimensional Brownian motion, so if you look at this process here, you can think of it as a process in R3. If you think of this process here, this is a Markov process. As I said, you can think of it as a process in R3 because you've got three components. But truly, you should think of R3 as being a different kind of space, meaning it's not really R3 with your usual standard addition. This is going to be, you can put a group structure, which is somehow more natural on R3. What do I mean by more natural? I mean the following, in the following way. You can put a group structure on this space so that then you can talk about left invariant vector fields on that space. And you can take this operator here. This is a second order differential operator, sum of the squares. And what it turns out is that this operator here is the generator of this Markov process. That's what that's kind of that's really the reason why because if you only think about it, if you only take your vector fields to be dx, dy, dz, and then you look at the sum of the squares, then the generator corresponding to this, the operator that would correspond to this would be just the Laplacian on R3. And you know that pretty much the process that corresponds to the Laplacian is just a standard Brownian motion B1, B2, B3. So what we are doing here, it's kind of, which is what I'm not really trying not to stress too much, but you're changing the geometry of R3 so that you get a geometry which is not non-abelian, but it's not in a way that if you look at this operator here, the sum of the left invariant vector fields, this would correspond naturally to this process. And again, the reason why we have chosen this process here is because we are pretty much embedding the third component, which is the Levy area, in a way that this whole thing is now Markov. Or just take this as a grant. This is a stochastic process. The nice thing is that it satisfies some sort of scaling, which we like because it gives you an onset of what you have to prove. Unfortunately, it's not a Gaussian process, but you can still do things with it. And the first result I wanted to mention was in a paper a few years ago now. We pretty much solved the small deviation principle for this process here. And should mention the proof here is completely probabilistic. And in a way, the proof here is what inspired us then later to do the proof for time-dependent spherical random fields. Because really what you're doing here, you're using the explicit expression for this process, and then you're using heavily Borel-Cantelli. And the idea was to first prove Chung's law, and then once you have Chung's law, you can go back and prove the small deviation. So you're going back and forth. So it's great because it's very easy to read. Unfortunately, it doesn't tell you anything about what's this number C. We were able to prove that C is positive, it's finite. We got an explicit bound, but we don't know what's the value of C squared. Unfortunately.
Marco, by the modulus of G here, you mean the square root of the sum of squares?
You mean the modulo here?
Yeah.
No, I do not. That's a good. I was being a bit like vague about that. So this is a norm which is consistent with the geometry on the new space. So you have a different scaling now because somehow when you're in this space here, your Z component scales in a different way. So the norm looks like this. You have a lot of different norms. One norm you can choose is the norm x, y, z is, let's say, to the power of 4, you got x squared plus y square plus z square. So the norm is what you would expect. So on the x and y on the plane or horizontal plane on R2, x and y, you pretty much have your Euclidean in some sense. But then you see that the third component scales differently.
So this doesn't tell you anything explicitly about your original xt, right? It gives you this.
No, well, we knew
get this connection here.
Well, we knew. So if you only look at xt by itself, we did know everything. We knew that it was. We knew its small deviation, and we know the Chung's law. So what we were going after was. It wasn't just the Lévy area, it was this whole process here. Just sort of like the question that what we had in mind was, now the Lévy area is not a Markov process, and Rémillard proved small deviation and Chung's law. What we wanted to see was, okay, we have a process now which somehow takes into account the Lévy area and its Markov. And so our the question that we had was, how is the spectral gap of this operator here related to the small deviation of this process here? That's what we were thinking. And the first result, it doesn't prove that. It doesn't, in some sense, it tells you that this is the correct rate, which somehow is not surprising in this for this process here, but yeah, it doesn't tell you much about the. It doesn't answer the question that we were having at the very beginning, whether can we recover some spectral properties of this operator. But that was solved. Thankfully, we were able to solve that a few years later. We did answer the question, meaning that we were able to prove that this number here is indeed, let's call it again, maybe λ1, where now this λ1 would be the first eigenvalue corresponding to this process here. And as I said, the proof of the first result, this is purely probabilistic, pretty much relies on Borel-Cantelli plus the explicit expression for this process. Whereas the proof here is in spirit is very similar to the one I showed you for the Brownian motion. So you rely on you need to write the transition density of the Hill process, but then you have to prove that you have some kind of eigenfunction expansion for that, which really boils down to proving spectral properties for this operator here. And it should mention it's done in a more general context, not just for the atomic group. It's done for a more general class of processes. But we were able to prove that for that type of processes, the small deviation, it does give you the spectral gap of the corresponding generator. Should also mention, maybe I should have mentioned this earlier, this is it's a hypoelliptic operator because X and Y satisfy our boundary conditions. So you also have a smooth transition density here, and things are not too bad. So yeah, the answer, we were kind of excited because we thought, okay, maybe there's this general thing that give me a Markov process, look at the small deviation, and you're gonna get the spectral gap of the generator. That was kind of the what we had in mind, and that's now the next. Yeah, this one, the next example sort of tells you that that is not the case in general. So this is going back to Xi's question from earlier. Let's say you take this very simple process. This is definitely not a Markov process. So what you can do is, if you want to make it into a Markov process, is to look at this new pair here. Now, if you look at Brownian motion of time t and its time interval, this is it's a Markov process. It's called Kolmogorov diffusion, step 2 Kolmogorov diffusion, and it's sort of an interesting story because so let me tell you, I said it's Markov, and you have a very explicit generator here. And from what I heard, like this like folklore, why was Kolmogorov interested in? This seems like a very simple process, and apparently at that time there was this idea that for a Markov process to have a transition density, the generator should be somehow regular, elliptic. And so this is a very surprising fact at the time. This was done in the 1920s, because Kolmogorov computed explicitly the transition density of this process. It showed that it's Gaussian. It's not an easy expression, but it's explicit, and its generator is highly degenerate. So it was a very surprising. So in other words, this is telling you that there exists a fundamental solution for the heat equation, even when the generator is degenerate, which was very surprising back at the time. Then in the 60s, Hormander used this in a seminal paper on hypoelliptic operators. He used this operator here as the simplest example of a hypoelliptic operators, which are exactly those operators where you have a smooth transition density of the corresponding process. But anyhow, so it's an interesting process. It's Gaussian. The negative side, though, is that you do not have a scaling property in this case. So it's not clear what the correct rate should be, because these two components, they have a different scaling. And so you can't really go with Borel-Cantelli, because usually you apply Borel-Cantelli when you have some global scaling for your process. On the other hand, you can't really go down the analytic route like we did in the previous for the Lévy area. And the reason is that this is a very degenerate operator. So it's also hypoelliptic. So they're both hypoelliptic, this one and the one from the previous slide. But somehow this is more hypoelliptic, more degenerate than the previous one, to the extent that if you look at the semigroup corresponding to this operator here, that might not even be symmetric. It's very highly degenerate, and spectral theory for this operator is highly non-trivial. So you cannot use Borel-Cantelli, and you cannot rely on analytic properties. but we were still able to compute explicitly the small deviation in Chung's law. So this is interesting because for now, this is the first example that I'm showing you that the rates are very different. In all the previous examples, the rate were, 2/3 and 3/2, 2 and 1/2. Whereas now they're very different in the sense that the small deviation behaves exactly like the first component, whereas Chung's law behaves exactly like the last component. Here, think of n as being 2, and look at this one here. So yeah, very different behaviors. And in some sense, it also gives an answer to the question that we had, because the thing on the left is the small deviation for a Markov process, which has an explicit generator. But unfortunately, the thing on the right, it doesn't see the generator, because the thing on the right here, this is nothing but the first eigenvalue for the generator of a one-dimensional Brownian motion. And this is true for a more general process, not just this one here. So in some sense, it's a negative answer that if you have a process whose generator is very, very degenerate, you don't really recover the spectral gap from there.
Another question, Marco.
Yeah.
It's nice. You have t going to infinity. Is there a corresponding result for t going to 0?
I've been trying to think. I've thought about that. There's one estimate that at some point I was thinking about that, because the thing on the right, it doesn't depend on n, right? Which is something that I found very fascinating. But unfortunately, if you don't take the limit over epsilon, it does depend on n. So it's kind of when you're taking the limit as epsilon goes to 0, you're killing all the components after. So only the first component survives. So maybe I should go back to it and I think about it, but maybe there's a way that you can control that so they can let maybe n go to infinity first and then take a limit over epsilon or something. But it's crucial that when you're taking the limit over epsilon, you're really killing everything, like all the other ones. It's kind of like magic, the way it works. But I wanted to tell you, there is an idea behind this proof that I think is very interesting. As I said, it doesn't rely on Borel-Cantelli and it doesn't rely on any analytic property. So what we use is what's known as Gaussian correlation inequality, which I'll tell you something about. So this is an inequality which was conjectured in the 1955 or like 40s, 50s. And then I've noticed that, especially in the small ball business, in the 90s, late 90s, there were a lot of papers that were proving results assuming this inequality here. So what the inequality says the following. Let's say you have X, which is a Banach space. And then you take two subsets A and B, which are, you need them to be convex and symmetric with respect to the origin. So if X is in A, then negative X has to be in A as well. And you fix mu to be any, this is a centered Gaussian measure. Then the estimate says that if you look at the measure of the intersection of A and B, this is always greater or equal than the product of the measures. The way this is used in the proof, you're using the fact that the Kolmogorov diffusion is a Gaussian process. And so you would simply take mu to be the law of the Kolmogorov diffusion, X to be the space of path, and then you get a good estimate from below on the probability that Kolmogorov diffusion is less than epsilon, and then you play with it. If you do some research about the history of this estimate, it's very interesting because apparently this was proven in 2014. but no one found out of it until 2017. So what happened behind the history behind this estimate is that it was proven by a German statistician, Royen, in 2014, but apparently it was published in a predatory journal, so no one like realized that it was proven. He proved a more general version of this estimate for some multivariate gamma distributions, but like we basically proved that, but no one noticed it until in 2017. Two other mathematicians, I forgot their names, they bump into Royen's proof and they realized that it was correct indeed, and it was, as a special example, special case of his proof, you would recover this estimate here. The proof by Royen is for Gaussian measures in Rn, but then it easily extends to like on Banach spaces. But it's I think it's worth it could be a very powerful tool to use in the Gaussian world. Realizing that time, 20 minutes. So let me move now to the time-dependent spherical random fields. Actually, before that, just a few comments about random fields. This is exactly the same slides we had at the beginning. All I'm saying is that if you have a random field, we're going to introduce this. There's this distance here, which is just a distance induced by the field, and we're going to have some assumption on the estimate on some bounds on this distance. So far, I've only gave you results for processes, what is known for fields. A lot of things are known. I'm just mentioning things related to the work I want to present later. If you have a real valued Gaussian random field with stationary increments, then you want to make two assumptions. So the first assumption here, it simply says that the distance induced by the field is comparable to some distance. And then you need an assumption which is purely probabilistic. And it seems like a very weird assumption, but they do provide, in this paper here by Luan and Shao, they do give a lot of examples of processes where this is satisfied. For example, the fractional Brownian motion is there, like the Brownian sheet, things like that are also there. But under these two assumptions here, they were able to prove a law of iterated logarithm, Chung's law of iterated logarithm for a random field. And here the constant, well, this constant again, not known, but Q is explicit and it depends on this norm that is controlling the pseudo distance. This was pretty much what inspired our work, because we saw this, we're like, okay, now you're not going to be surprised to see that before proving Chung's law, in a previous paper, they proved small deviations, pretty much small probability. So in the previous result, they provided upper and lower bounds on this probability here, which is a slightly weaker version of the small probability that I gave you, meaning that from this estimate here, you have that pretty much epsilon to the Q is the correct rate, meaning that the limit is positive and the limit sup is finite. You don't get that the limit necessarily exists, but having this, it's enough to allow you to go from small deviations to Chung's law. Yeah, this was done a while ago. So this is pretty much what we know about random fields, Gaussian random fields with stationary increments. So what we decided to look at was time-dependent spherical random fields. What are those? So you basically have a random field, which is defined on the sphere cross time. So in each point xt, you have a random variable. And you make two assumptions which are reasonable. Well, one is reasonable, the other one we would like to get rid of it. eventually, but for now, what we have is that this is isotropic in space and stationary in time. So what that means is that in distribution, the random variable, it doesn't matter if what point on the sphere is, you can rotate and it doesn't change the distribution, or you can shift in time and that also does not change the distribution. Why do we like what a nice consequence of having a isotropic spherical random fields and also in time is that you can decompose them very nicely, and you have a very nice sort of like a Fourier decomposition. When I get to the theorem, you can think of this as pretty much Fourier analysis, but on S2. And what it turns out is that on the spatial time here, you have this nothing is random in space. The randomness is only in time, and here you have a sequence of stationary Gaussian processes. So this is the model that we have. So you take this object here, where x is a point on the sphere, t is a point on the real line, or 0 and 1. What assumption do we have? So we made pretty much assumptions so that when we restrict to, because here, if you're freezing, if you freeze the x variable, you have something which is just a Gaussian stationary field. So the assumption that we made was that done in a way that if you're freezing the spatial variable, you're back in the assumptions that Luan and Shao had just for classical for classical fields. So the first thing is about the behavior of the covariance. This is the covariance of ALM. This should actually be, they don't have to be equal, but roughly as the time gets smaller and smaller, as tau gets smaller and smaller, you want to behave like this function here. And this makes it consistent with Luan and Shao. And then the other condition that we have is on the asymptotic behavior of this coefficient as L goes to infinity. And just show you, so they have a behavior of this type, and this is true for some alpha in this range. Now, might not have too much time to tell you about this, but when alpha less than 4, this is not restrictive in the sense that this is what it's expected. It goes back to a paper from 2018 by Marinucci, Luan, and Shao. So where they explain that you do want alpha less than 4. I personally believe that the condition alpha greater than 2 plus beta is artificial in the sense that I believe that this is the correct statement. It should be true for any alpha in 2 and 4, because that's the same range that they have in a previous paper, which is dealing only with spherical random fields without the time component. Unfortunately, for one technical proof to work, we have to be a bit far from 2. You can't you need this. You cannot take beta to be 0. Then what do? You introduce a weird function, which I don't want you to look at. The only thing I want you to keep in mind is that this is explicit. And when you're freezing this space, so if x is equal to y, this thing is 0, so that you're left with a function, that looks like the function that Luan and Shao had for spatial, for just Gaussian fields on Rn. Again, don't look at the actual expression. What I want you to keep in mind, this is explicit, and what we proved as a preliminary result is that this explicit function here, it controls the distance induced by the field. So we needed something explicit to do some computation. So you take the distance induced by the field, and you can prove that it's bounded by this explicit, not so pleasant, but explicit function. So that's the first preliminary result. And the second one is that you do have a, this is very similar to the assumption that Luan and Shao had on Gaussian fields. So we proved it for time-dependent spherical fields. I should mention that this estimate, this sort of estimate here, it is known for purely if you have a field that only depends on which is only spherical field. This was proven in 2018 by Luan, Shao, and Marinucci. And in that paper, they have the assumption that alpha is in between 2 and 4, and pretty much the take home there is that for alpha greater than 4, this should not hold. For alpha in between 2 and 4, they prove that this estimate on the variance is true. And the only case that they have open is alpha equal 4, which is not known whether this estimate holds. But what we did, we were looking at time-dependent spherical fields and using the result on the non-time-dependent spherical fields, on purely spherical fields, we proved this. And once you have these two things, what we did was trying to adjust the proof by Luan and Shao on Gaussian fields on this new setting here. So the result that we have, yeah, this is the paper that I mentioned for this condition. The result that we have is under those conditions on the field, so that alpha is in between 2 plus beta and 4, and the covariance has a certain decay, we were able to prove Chung's law and small deviation, where now the exponent is explicit. Again, this constant, it is not explicit. What I can tell you about this constant for sure is that it does not depend on xt. So here you're fixing a point xt, and heuristically, the reason why it doesn't depend on xt is because we're dealing with isotropic stationary fields. So it doesn't really matter where you're positioned in some sense. In distribution, it would be the same. So that's why it doesn't depend on that. We're currently working on dropping the stationary assumption. And in that case, I would expect this to depend on time if you drop the stationary. So I want to have a few minutes to just one quick idea on the proof. Set this notation here. You want to estimate this thing here, right? So the first step, just want to mention this heavily relies on Talleyrand's bounds. So there are very beautiful papers and results by Talleyrand on how to estimate the probability that a Gaussian field is less than some constant. And so the other reason why the constant that we have here is not, where is it? This is not explicit is because the constant here heavily depends, on constants that you get by applying Talleyrand's bounds. So you rely on Talleyrand's estimate, and you're able to prove an estimate of this sort. Now, once you have this kind of estimate, you're not done. This is halfway through the small deviation, because from this, what it would follow that you're almost there. You know what's the correct rate. You know that the lim is positive, lim sup is finite, but you really want this limit to exist. So you're not there yet. So what we did, we were like, okay, we've got this. Then we looked at Chung's law, and we were able to prove that this quantity here, ideally you want this to be a constant number, which is positive and finite. Using these bounds, we were able to prove that it is finite and positive, but we were not able to prove it was constant. So we were kind of like stuck for a while with we are halfway there with both laws, but we were not able to conclude them. And so the last step that we did, and this was inspired by the paper on the Eisenberg group for the Levy area, was to look at this weird thing here, this objects, and which from these bounds, it would follow that this is finite and this is positive. And the idea was to connect this number with these two numbers here. More precisely, using Borel-Cantelli, and that's where I use Borel-Cantelli, you can prove these two estimates. What makes it tricky is that, as usual, one of the two Borel-Cantelli lemmas that doesn't rely on independent events, which would correspond to this estimate here. So this estimate is always, it's a bit easier. Then you have to do some work to get the other estimate, because you have to construct things which are not dependent. Sorry, you have to construct things, yeah, you have to construct events which are independent, and you prove this. But once you have this, it follows as a byproduct that then this constant k has to be this random variable k has to be constant, because clearly C minus is less or equal than C plus. So you've squeezed it. And once you have that, you get as a byproduct also that C minus is equal to C plus. And so that tells you that you were able to prove the small deviation. So it's kind of you get two birds with one stone at the very end. We were halfway done until most of the proof for step 1 and 2, and then we were able to make it work. And that's pretty much where I might be a bit over time, but that's where I wanted to stop. Thank you.
Thank you. Thank you very much, Marco. We have got a couple of minutes for questions. So please.
Marco, everything you've talked about is for Brownian motion, but all the questions make sense for a Levy process, for example.
There's no Levy process. I believe I must have run at some point in a paper about small probabilities for Levy processes. It is there is more literature. I only kind of like gave you like things that like I needed, but definitely the Levy processes are
it'd be interesting to look at. There is a Chung law for Levy processes at 0.
Yeah.
It was proved by Boris Berkman and myself back in 2011.
Okay.
Yeah. And we have other results on Levy processes, generally with small time behavior or more generally point process results. That a lot of those, I think, would carry over to what you're doing in some form or another.
Mm-hmm. You know, I do remember a few papers on. I have not seen the one on point processes, but I do remember very clearly like the Levy processes or like alpha stable processes, things like that. There's a lot known in that direction too. Yeah. Yeah,
we also have some papers on upper and lower bounds for Levy, normalized Levy processes and so on. Yeah, you can follow those up quite easily.
Mm-hmm. Thanks.
Mark, thanks, very nice talk. I have a question about this, you told strange conditions. So they are quite well known about local non-determinism and all other things. Yeah. So usually these conditions, of course, directly difficult to check, but Shao and others, they develop some methods where you can just check conditions on spectral densities. So do you have results of this type?
We do not. No, because we were kind of the way we got back to so the way we proved this was pretty much really relying on what was known on the wait, am I? Yes, okay. It was done by looking at what is known on the spherical case. So we just like adjusted, like we used what the result that we knew from here, which work on S2, and we just pretty much went from S2 cross R to S2. That's kind of how we did it. We didn't like I've seen in the paper by Shao one that they have more general, like definitely a more general way approach of like checking this estimate. But I think in our case this is why it was just a lemma. It was relatively simple to like prove this condition because it really relies on the fact that you have it on S2, and but maybe that would make sense on more general, like if you have maybe like a manifold times R or something like a more general like setting, you might want something more general. But in this case, this was I don't want to say this was straightforward, but it was really relying on this heavily on this paper here. Yeah.
Okay. And maybe a quick another question. So you mentioned these results by Talleyrand, and if I understood correctly, so it was done for not only for Gaussian but also for sub-Gaussian. So all such inequalities, they exist for different classes of sub-Gaussian random fields. Do you think that it's possible somehow to extend to these things as well?
I did not know about. I only knew about this kind of estimate for Gaussian, which is why we just went immediately for like just okay, let's look at Gaussian, because if you without Talleyrand's bounds, you can't like it's sort of like you don't know where to begin. That was sort of like the thing. But if you're telling me that you have something like this for things which are sub-Gaussian, or I think there might be hope to like make it, change a few things so that it works. I was not aware of like there was a whole bunch of things. That's
okay. Thank you.
Okay, so thanks again. No further questions. Let's thank our speaker again. And hopefully there will be further seminars soon. Just watch this space. Thank you.
Thank you.